The year is 2023. Something strange happened to Voyager 1, a spacecraft more than 14 billion miles from Earth. It suddenly stopped sending normal messages. Instead of clear data, only a stream of random numbers came through. For months, no one knew if the spacecraft was alive or lost forever. The problem was inside its memory system, like a computer whose files had become scrambled after nearly half a century in space. Engineers on Earth refused to give up. They carefully found a way to move Voyager's operating code into a different part of its memory, one that was still healthy. After many long weeks of sleepless nights, a clear signal returned. Voyager 1 was talking again, and the information it sent back was more than just a relief. It revealed incredible details about the edge of our solar system, discoveries so mysterious that scientists are still trying to understand them today. Leave a like and subscribe to the channel as we begin the story of those mysterious discoveries, and of the tiny machine that carries humanity's curiosity into the endless dark. More than 45 years after leaving Earth, Voyager 1 has reached a place no other human-made object has ever explored. This region has no map. There are no planets, no moons, no comforting landmarks. Only a vast emptiness between our solar system and the wider galaxy. Scientists call the outer skin of our solar bubble the heliosphere. It is formed by the solar wind, a constant stream of charged particles flowing outward from the sun. For billions of miles, this wind pushes back the thin gas of interstellar space, creating a giant protective bubble around everything we know. Voyager 1 is now far beyond the orbit of Pluto, more than 14 billion miles from home. Out here, the sun is only a pale star, barely brighter than the others. Yet, even in this emptiness, the spacecraft's instruments have been recording something astonishing. For decades, scientists pictured the edge of the heliosphere as a gentle fade, like smoke thinning in the air. But Voyager discovered something very different. As it approached the true boundary, it encountered a sudden, sharp change. Inside the bubble, the solar wind blows outward at hundreds of kilometers per second. Then, almost without warning, that outward flow drops nearly to zero. Beyond this point, the particles from distant stars dominate instead of the sun. Voyager crossed that invisible wall in August 2012, becoming the first messenger to step into interstellar space. The data shocked scientists. The density of particles outside was much higher than expected, almost like walking from a quiet hallway into a crowded room. Magnetic fields twisted in unexpected directions. And even though the solar wind had stopped pushing outward, Voyager could still sense occasional bursts of solar activity rippling across the boundary, like waves striking the hull of a ship. Perhaps the most eerie discovery was a faint, constant plasma hum. Voyager's plasma wave instrument detected a steady vibration in the charged gas surrounding the spacecraft. It is not sound in the way we hear on Earth. It is an electromagnetic signal, a slow, ghostly tone that has persisted for years. Scientists say this hum comes from the thin gas of the galaxy itself, a whisper from the space between the stars. Hearing it for the first time gave many researchers chills. This is not the voice of our sun. This is the background music of the Milky Way. Even beyond the heliopause, Voyager still feels the sun's influence. Powerful solar eruptions send shock waves racing outward. When these waves reach Voyager, sometimes years after the event, they create sudden spikes in plasma density. By timing these spikes, scientists can measure how far the sun's reach extends. Each measurement redraws the limits of our solar neighborhood. These findings changed how scientists think about our cosmic bubble. Instead of a smooth, round shell, The heliosphere appears lumpy and dynamic, shaped by magnetic fields and streams of interstellar gas. Some regions bulge outward, others are pressed inward. The edge is alive, constantly shifting like the surface of an ocean. For future missions leaving the solar system, this matters. They will face varying conditions, areas of thicker or thinner plasma, stronger or weaker magnetic fields. Voyager's readings provide the first real guide through this frontier. It is easy to forget how small Voyager is. The spacecraft is about the size of a small car, with a 3.7-meter dish antenna and a long boom carrying its instruments. Its power comes from 3 radioisotope generators, small nuclear batteries that have been slowly fading since launch in 1977. Yet this aging machine, traveling at more than 17 kilometers per second, is still gathering priceless information about a region no human has seen. Even now, every bit of data takes more than 22 hours to reach Earth. The signal is weaker than a whisper from across the continent, captured by giant antennas of NASA's Deep Space Network. Each packet of information is a treasure, evidence of how our solar system meets the galaxy beyond. As if to remind us how fragile this mission is, in November 2023 Voyager 1 suddenly began sending nothing but unreadable numbers. After decades of faithful service, its memory system had developed a fault. For months, engineers tried to find a solution, sending carefully planned commands and waiting almost 2 days for each round-trip response. Finally, in April 2024, they succeeded in moving the operating software into a healthy part of the spacecraft's memory. The signal cleared. Voyager was alive. The relief was enormous, but the data that followed was even more exciting. The spacecraft continued to detect the steady hum of interstellar plasma, along with new details about the shifting magnetic fields and changing particle densities just outside the solar bubble. These fresh measurements help scientists refine their picture of the heliosphere's shape and how it protects the planet's inside. Why should anyone care about a faint hum or a change in particle density billions of miles away? Because the heliosphere acts as a shield for Earth and every other planet. It deflects much of the dangerous cosmic radiation that fills the galaxy. By learning how this shield works and how it might weaken or strengthen, we gain insight into the long-term habitability of worlds inside our system, including our own. Voyager's discoveries also touch something deeper. They remind us that our sun is not isolated. It sails through the Milky Way, surrounded by a vast ocean of interstellar gas and magnetic currents. The edge of the solar system is not the end of space. It is the beginning of the galaxy. As Voyager continues outward, its power slowly fades. Engineers expect the instruments to fall silent sometime in the next few years. But until that final moment, every new reading is a step farther into the unknown. The spacecraft is still moving at more than 38,000 miles per hour, carrying a golden record of Earth's sounds and music, our cosmic calling card, to any intelligent beings it might someday pass. The edge of the solar system has already surprised us. What secrets might still wait in the vast interstellar space ahead? Could there be unexpected currents, hidden structures, or clues about how other stars shape their own protective bubbles? These are the questions that keep scientists awake at night. Voyager has crossed the boundary and shown us the first hints of the wider galaxy. But to understand how it all began, we need to travel back to the mission's earliest days, when engineers dared to imagine that a small probe could one day touch the stars. Long before Voyager reached the edge of the solar system, it had to escape the cradle of Earth. The mission began in the early 1970s, when a rare planetary alignment offered a chance that comes only once every 175 years. Jupiter, Saturn, Uranus, and Neptune would line up in such a way that a spacecraft could visit each world in turn. using the gravity of one planet to slingshot to the next. Engineers called this path the Grand Tour. With clever planning, a single spacecraft could explore the entire outer solar system instead of launching separate probes to each planet. The idea was bold and the timetable tight. NASA scientists and engineers had to design a spacecraft that could survive for more than a decade in deep space, travel billions of miles, and send back reliable data with technology that would quickly become outdated. They settled on a pair of nearly identical probes, Voyager 1 and Voyager 2, each carrying cameras, spectrometers, magnetometers, and instruments to measure charged particles and plasma waves. To ensure communication across such vast distances, each spacecraft was fitted with a large 3.7-meter dish antenna. Power would come from 3 nuclear batteries, known as radioisotope thermoelectric generators, which could supply electricity for decades without sunlight. Voyager 2 launched first on August 20, 1977, followed by Voyager 1 on September 5. Despite the numbering, Voyager 1 was given a faster trajectory that allowed it to reach Jupiter first. Within weeks, the spacecraft were speeding beyond the orbit of Mars, their golden records safely attached to their sides. Each record carried sounds, images, and greetings from Earth in dozens of languages. A message in a bottle for any intelligent life that might someday find them. The first destination was Jupiter, the largest planet in the solar system. Even before arrival, Voyager's instruments began sending back surprises. The magnetic field around Jupiter was stronger and more complex than expected, and the planet's radiation belts were intense enough to endanger spacecraft electronics. But the real excitement came from the moons. Voyager revealed volcanic eruptions on Io, the first active volcanoes seen beyond Earth. It showed the cracked, icy surface of Europa, hinting at a hidden ocean beneath. Ganymede and Callisto displayed landscapes scarred by impacts and ancient tectonic activity. Each moon was a world of its own, breaking the simple picture of frozen, dead satellites. After Jupiter, Voyager 1 set course for Saturn. Here too the discoveries came quickly. The planet's rings, once thought to be simple flat bands, were revealed as intricate structures of countless icy particles, with gaps, spokes, and wave patterns shaped by tiny embedded moons. Voyager found new moons as well, some no larger than mountains. Most intriguing of all was Titan, Saturn's largest moon, wrapped in a dense orange haze. Instruments detected methane in the atmosphere and temperatures near the point where methane can be liquid, suggesting rivers and lakes of this exotic substance on the surface. Titan became one of the most Earth-like environments in the solar system, though far colder and stranger. Voyager 1's mission plan ended with Saturn, but the spacecraft's speed and trajectory would carry it upward out of the plane of the planets, on a path toward the outer edge of the solar system. Voyager 2 continued on to Uranus and Neptune, completing the Grand Tour, but Voyager 1 was already becoming our pioneer into the deep beyond. By 1990, it was more than 3.5 billion miles from Earth, far enough for its cameras to capture the famous pale blue image, a tiny speck of light that held all of human history. Soon after, the cameras were turned off to save power, but the mission continued with other instruments. Through the 1990s and early 2000s, Voyager 1 kept moving outward. Scientists watched the signals carefully, waiting for signs that the spacecraft was approaching the outer boundary of the heliosphere. They expected a slow decline in the solar wind and a gradual increase in cosmic rays. Instead, Voyager encountered unexpected shocks and sudden changes. In 2004, it crossed a region called the termination shock, where the solar wind slows abruptly and begins to mix with interstellar particles. Then came the heliosheath, a turbulent zone where solar and galactic forces wrestle for control. Measurements here showed strange magnetic field directions and particle flows that challenged existing models. These findings set the stage for the dramatic moment when Voyager finally broke free of the sun's influence. Scientists now knew that the boundary was not a smooth shell but a shifting, dynamic frontier. They debated when the final crossing would occur, and for months every new reading from the spacecraft was cause for excitement. By the time Voyager 1 confirmed its passage into interstellar space in 2012, it had already rewritten textbooks about the outer solar system. All the while, the spacecraft itself remained remarkably healthy. Its instruments aged, but careful management allowed engineers to stretch every watt of power. Commands were sent across billions of miles, each one taking over 20 hours to arrive. A single misstep could mean the loss of the mission, yet the team kept Voyager operating year after year. Every measurement added to our understanding of how the sun interacts with the galaxy, how cosmic rays are filtered, and how future explorers might one day leave the safety of our stellar neighborhood. The grand tour that began as a planetary mission had turned into something far greater: humanity's first direct contact with the space between the stars. Voyager 1 carried with it not just instruments and sensors, but the hopes of a species eager to know what lies beyond. The discoveries made along the way, the volcanic fury of Io, the hidden seas of Europa, the methane skies of Titan, the sharp boundary of the heliopause, were steps on a journey that continues even now. As Voyager travels farther into the interstellar medium, its power slowly fades, but its message endures. Each bit of data is a reminder of how far we have come and how much more there is to explore. The spacecraft may be small, but it represents the reach of human curiosity, a silent traveler carrying the voices and music of Earth across the endless dark. Its path through Jupiter's storms and Saturn's rings was only the beginning. The true challenge lies ahead, in the cold depths where the influence of the sun gives way to the currents of the galaxy itself. Even after decades of flight, Voyager still teaches us that exploration is not just about reaching a destination. It is about listening to the universe, noticing the unexpected, and daring to send our questions into the unknown. The edge of the solar system is not an ending but an invitation. What Voyager has already found at that frontier is remarkable, yet the greatest discoveries may still be waiting in the interstellar night. By 2012, Voyager 1 had left the protective bubble of the sun and entered the wider ocean of the galaxy. For the first time in human history, a machine built on Earth was sailing through true interstellar space. Scientists marked the moment with excitement, but crossing the heliopause, the boundary between the solar wind and the interstellar medium, was not like stepping across a sharp line on a map. It was more like pushing through layers of invisible surf, each wave carrying its own surprises. Inside the heliosphere, the sun rules. Charged particles stream outward in a constant flow called the solar wind, creating a bubble that shields the planets from a large portion of the galaxy's high-energy radiation. Outside, the environment is harsher and older. The interstellar medium is a thin soup of atoms, dust, and magnetic fields left behind by ancient stars that exploded long before the sun was born. Voyager's crossing gave scientists their first direct taste of this alien environment. The signs came gradually. First, the spacecraft recorded a dramatic increase in cosmic rays, high-energy particles that travel across the galaxy at nearly the speed of light. Inside the heliosphere, the sun's magnetic field deflects many of these rays. Outside, there is no such protection, and the counts climbed sharply. At the same time, the familiar solar wind disappeared. Instruments that had long measured the outward flow of particles suddenly detected none at all. Instead, Voyager's plasma wave detector picked up a faint, eerie hum. vibrations in the sparse interstellar gas, like the whisper of a vast, unseen ocean. These measurements confirmed that Voyager was beyond the sun's reach. But the crossing also revealed puzzles. The magnetic field around the spacecraft did not rotate as sharply as models predicted. Instead of a clean break, the field seemed to bend and twist, as if the sun and the galaxy were locked in a slow, ongoing tug-of-war. Scientists realized that the heliopause is not a solid shell but a shifting boundary, shaped by solar activity and the pressure of nearby interstellar clouds. It breathes in and out as the sun's 11-year activity cycle strengthens and weakens the solar wind. Voyager's data allowed researchers to estimate the density and temperature of the interstellar plasma. They found it was warmer and denser than expected, around 50,000 degrees Celsius, but so thin that a cubic centimeter contains only a few atoms. In this nearly perfect vacuum, a single hydrogen atom can drift for miles without hitting another. Yet even in such emptiness, Voyager can detect subtle changes in pressure and magnetic direction. Every tiny signal helps scientists map the shape of the heliosphere, a task that had been purely theoretical before the spacecraft's arrival. The interstellar medium is not empty of stories. Many of its atoms were forged in stars that lived and died billions of years ago. When supernovae explode, they scatter heavy elements like carbon, oxygen, and iron into space, seeding future generations of stars and planets. The atoms that Voyager now measures are the raw material of worlds yet to be born. In a sense, the spacecraft is traveling through the ashes of long-dead suns, sampling the ingredients from which our own solar system once formed. Life in interstellar space is harsh. The temperature hovers just a few degrees above absolute zero. The sun is no longer a blazing disk but a bright star among countless others. From Voyager's viewpoint, Earth is a speck lost in the Milky Way's pale glow. Yet the spacecraft continues to function, powered by the slow decay of its nuclear batteries. Each year, the available energy drops slightly, forcing mission planners to shut down one instrument after another to keep the most vital systems alive. They carefully weigh each decision, knowing that once a device is turned off, it can never be restarted. Despite the fading power, the science continues. Voyager measures the density of interstellar plasma by listening for natural radio waves generated by distant events. When a solar storm erupts on the sun, it sends shock waves that eventually reach the heliopause, causing the surrounding gas to vibrate. Voyager records these vibrations months or years after the storm, giving scientists a delayed but valuable report on solar activity. These echoes from the sun help researchers understand how our star interacts with the galaxy and how cosmic rays travel through space. One of the most surprising findings is that the pressure of the interstellar medium is higher than expected. This means the heliosphere, our solar system's protective bubble, is being squeezed more tightly than models predicted. Understanding this balance is important not just for astronomy but for future space travel. Any crewed mission that one day ventures beyond the heliosphere will need to know how radiation levels change and how to shield against the constant rain of cosmic particles. Voyager's journey also offers clues about the structure of the galaxy itself. By measuring the direction and strength of magnetic fields, the spacecraft helps scientists trace the enormous loops and filaments of magnetism that thread through the Milky Way. These magnetic highways guide cosmic rays, influence star formation, and shape the clouds of gas between stars. Before Voyager, such measurements could only be inferred from distant observations. Now we have a probe in the field, slowly sending back first-hand reports. The communication link between Voyager and Earth is an achievement in itself. Signals from the spacecraft, traveling at the speed of light, take more than 22 hours to reach the deep space network antennas on Earth. Engineers must wait almost 2 days to send a command and receive confirmation. The transmitter aboard Voyager produces less power than a refrigerator light bulb, yet the giant radio dishes on Earth can detect its faint whisper across more than 20 billion kilometers of space. This ability to maintain contact over such distances is a triumph of engineering, proof that human ingenuity can bridge almost unimaginable gaps. As the years pass, the mission team faces hard choices. Power levels continue to drop, and each winter more instruments must be turned off. The cosmic ray detector may be next, followed eventually by the plasma wave instrument. Engineers hope to keep at least one scientific sensor operating until the early 2030s, but by then the spacecraft will likely fall silent. Long before that day, they will also shut down the heaters that keep Voyager's electronics warm. In the freezing darkness of interstellar space, the temperature will plunge, and circuits will eventually fail. Even after the last signal is received, Voyager's journey will continue. The spacecraft will coast through the galaxy for billions of years, circling the center of the Milky Way like a tiny metal seed. Long after Earth itself is gone, Voyager will still be out there, carrying the golden record with its music, images, and greetings. In this way, the mission is both a scientific exploration and a time capsule, a message to whoever might someday find it. The golden record remains one of the most poetic elements of the mission. Etched in copper and coated with gold to resist the ravages of time, it contains greetings in 55 languages, sounds of wind and water, and a selection of music from around the world. There are photographs of landscapes, animals, and people, as well as scientific diagrams that explain where the spacecraft came from. The record's designers knew the odds of discovery were small, but they wanted to send a gift anyway, a reminder that Earth once existed and that life once reached for the stars. Voyager's continuing reports from interstellar space have changed the way scientists view our place in the galaxy. We now know that the sun's protective bubble is more complex and dynamic than anyone guessed. We understand more about how cosmic rays penetrate the heliosphere, how interstellar clouds interact with stellar winds, and how the galaxy itself shapes the environment of every star system. These discoveries feed directly into models of space weather, helping to protect satellites and future explorers closer to home. Perhaps most important, Voyager demonstrates the value of long missions and patient science. When the spacecraft launched in 1977, no one could guarantee it would survive long enough to reach Jupiter, let alone the edge of the solar system. The engineers and scientists who built it had to think decades ahead, designing hardware and procedures that would outlast their own careers. Many of the people now commanding Voyager were children when it left Earth. The mission is a bridge across generations, proof that exploration can be a shared endeavor extending beyond any single lifetime. The crossing into interstellar space is not the end of Voyager's story, but the beginning of a new chapter. Each year it moves farther from the sun, deeper into the uncharted spaces between the stars. With every passing mile, it sends back clues about the environment our solar system sails through as it orbits the center of the Milky Way. These data points are more than numbers. They are the first touch of a vast, ancient realm that until now we could only imagine. Somewhere ahead lies the Oort cloud, a distant sphere of icy bodies that marks the outermost reaches of the sun's gravitational influence. Voyager will not reach that region for tens of thousands of years, and it will take more than 40,000 years to pass near another star. Long before those milestones, the spacecraft will go silent, leaving only its silent path as evidence of its passage. Yet even in silence, it will remain a symbol of what human beings can accomplish. a traveler that escaped the sun and stepped into the galaxy beyond. As we receive each faint signal, we are reminded that exploration is not a single event but a continuous process. Voyager teaches us that the universe is far larger and stranger than we once believed, and that the edge of the solar system is not an end but a gateway. The spacecraft carries no crew, yet it represents the curiosity of billions. Its lonely flight tells a story of persistence, discovery, and the unquenchable desire to know what lies beyond the next horizon. Keeping Voyager alive is as astonishing as the science it delivers. When the spacecraft launched in 1977, engineers hoped for a 4-year mission to visit Jupiter and Saturn. Anything beyond that was a bonus. Yet more than 4 decades later, the probe is still sending back data from a realm no human had ever measured. That longevity is not an accident or a miracle. It is the result of relentless planning, clever improvisation, and the quiet determination of many teams who refused to let the mission end. Every system aboard Voyager was built with endurance in mind, but nothing lasts forever. The spacecraft runs on 3 nuclear batteries, radioisotope thermoelectric generators, or RTGs, that slowly convert the heat of decaying plutonium into electricity. At launch, they produced about 470 watts of power, roughly enough to run a household blender. Each year, the output drops by a few watts as the plutonium cools and the thermocouples age. Today, the spacecraft receives less than half of its original power, barely enough to keep a handful of instruments operating and the transmitter strong enough to be heard across the void. From the moment the mission began, engineers knew they would face this slow decline. They designed Voyager with separate power lines and switches so individual instruments could be shut down one by one as the supply weakened. Over the decades, heaters have been turned off, cameras have been shut down, and backup systems have been disconnected to save energy. Each decision is carefully calculated. Which instrument provides the most valuable science for the least power? Which heater can be sacrificed without allowing critical components to freeze? The team meets regularly to debate these choices, knowing that every watt counts. Temperature is one of the greatest threats. In interstellar space, the ambient temperature is only a few degrees above absolute zero. Without heaters, fuel lines can freeze, lubricants can stiffen, and electronics can fail. Yet heaters draw power, and power is scarce. Engineers have learned to use the spacecraft itself as a shield. By rotating Voyager slightly or adjusting its orientation to the sun, they can trap small amounts of heat or expose certain areas to the faint warmth of the RTGs. These tiny maneuvers, planned with computer models and confirmed by years of experience, keep critical systems just warm enough to function. Communication is another constant challenge. Signals from Voyager take more than 22 hours to cross the gulf between the spacecraft and Earth. When controllers send a command, they must wait nearly 2 days to know whether it worked. A single typo or miscalculation could mean disaster. To guard against errors, every command is reviewed by multiple engineers before it is transmitted. The spacecraft's computer, with memory smaller than a modern digital watch, checks the instructions and compares them with stored safety routines before carrying them out. This slow, methodical process ensures that even after decades of silence between each command and response, the mission stays on course. Voyager's computer systems themselves are a triumph of 1970s technology. Each spacecraft carries 3 separate computers, one to control attitude and orientation, one to manage instruments, and one to handle communication and sequencing. These machines operate with only a few kilobytes of memory, far less than the storage inside a modern greeting card. Yet their simple architecture makes them surprisingly robust. The software can be rewritten from Earth to adapt to new situations, a feature that has saved the mission more than once. Over the years, engineers have uploaded new instructions to reroute data, bypass failing circuits, and even reprogram entire subsystems when hardware showed signs of wear. The 2023 communication crisis was one of the greatest tests of this adaptability. In November of that year, Voyager 1 began sending only a stream of meaningless numbers. Telemetry about its instruments and position vanished. For months, engineers on Earth struggled to diagnose the problem from billions of miles away. Using faint echoes and diagnostic signals, they finally traced the failure to a section of the onboard computer memory that stored critical command sequences. Something, perhaps a cosmic ray strike or simple aging, had corrupted the code. Without access to that memory, the spacecraft could no longer package its data for transmission. The solution required creativity. Since the faulty memory could not be repaired, engineers rewrote the operating software to store its vital code in a different, unused section of memory. This was like relocating the brain of a 1970s computer while it was still running, with no physical access and a 45-hour delay for each test and reply. After weeks of careful planning and countless late-night meetings, they sent the new commands. On April 18, 2024, a clear signal returned. Voyager was alive, its instruments reporting once again on the conditions of interstellar space. The mission had survived yet another brush with silence. Such victories depend not only on technology but on people. Many of the engineers who launched Voyager have long since retired, yet new generations have taken their place. Some of today's mission controllers were children when the spacecraft left Earth. They learned to read decades-old documentation, master outdated programming languages, and maintain equipment older than themselves. The Deep Space Network, the global array of giant radio antennas that listens for Voyager's faint signals, has also evolved. Modern digital receivers now detect signals billions of times weaker than a watch battery, but the basic task remains the same: hear a whisper across the vastness of space. Working on Voyager is a lesson in patience. Because signals travel at the speed of light, each exchange with the spacecraft takes nearly a day. Engineers cannot rush a repair or test a new command quickly. They plan every action carefully, run simulations, and wait for confirmation. This slow rhythm fosters a deep respect for precision. A single misstep might waste weeks of effort or even end the mission. Yet the team embraces the challenge, knowing that every new measurement from Voyager is unique and irreplaceable. The spacecraft itself helps by being remarkably reliable. Many of its components have lasted far beyond their expected lifetimes. The RTGs, though weaker, continue to provide steady power. The gyroscopes and thrusters that control orientation have fired thousands of times without failing. Even the digital tape recorders once used to store data during planetary flybys still function when needed. This durability speaks to the skill of the engineers who designed Voyager in an era when reliability was prized above all else. Despite the successes, the mission cannot continue forever. Power levels decline inexorably. Engineers estimate that by the early 2030s, they will have to shut down the last remaining scientific instruments. After that, only the transmitter and a few heaters may remain active, sending a simple heartbeat signal back to Earth. Eventually, even the transmitter will fall silent. Voyager will become a dark, silent object drifting through the galaxy, carrying its golden record and the last echoes of human contact. The thought of that final silence weighs heavily on the team. For many, Voyager is more than a spacecraft. It is a companion, a shared endeavor that has spanned careers and generations. Engineers speak of the probe with affection, calling it "she" or "our traveler." They celebrate every successful command and every new bit of data as if hearing from a distant friend. When the day comes that no signal returns, it will feel like saying goodbye to a member of the family. Yet even when Voyager's voice fades, its journey will continue. The spacecraft will drift through the Milky Way for billions of years, long after Earth itself is gone. Its path will carry it past the outer edge of the Oort cloud in about 300 years, and it will pass near another star in roughly 40,000 years. The golden record bolted to its side may survive for billions of years, carrying sounds of Earth, music, greetings, and the rush of wind and water through the endless dark. Long after our civilization changes beyond recognition, Voyager will still be out there, a silent ambassador from the late 20th century. The engineering effort to keep Voyager alive is more than a technical achievement. It is a testament to human curiosity and persistence. It shows that exploration is not just about powerful rockets or quick results. It is about patience, ingenuity, and the willingness to care for a machine that represents the best of us. Each faint signal that reaches the deep space network is a reminder that we can reach across unimaginable distances and keep a fragile connection alive. Voyager's survival also carries lessons for the future. As humanity plans missions to the outer planets, interstellar probes, and even crewed journeys beyond the moon, the techniques developed to maintain Voyager power management, remote software updates, long-term operations will guide new explorers. The mission has shown that hardware built with care and operated with creativity can endure for decades, carrying science and culture far beyond its expected reach. The engineers who now watch over Voyager know that they are caretakers of a legacy. They manage each watt of power, each line of code, each burst of data with the understanding that this mission will outlive them all. Their work ensures that the spacecraft remains not just a piece of hardware but a living story, a connection between generations, a bridge between the inner solar system and the great dark beyond. Every time a weak, 22-hour-old signal arrives at the Deep Space Network, it carries more than numbers. It carries proof that human beings, using technology no more advanced than the computers of the 1970s, managed to send a messenger across the threshold of the stars and keep it alive for nearly half a century. The Voyager team listens carefully to that signal, knowing that one day it will stop. But until then, they will continue to coax every bit of information from their distant traveler, celebrating each whisper from the edge of the galaxy. Voyager's lonely flight into interstellar space is not only a scientific triumph, it is a roadmap for the next great leap. Every measurement it sends back, every unexpected reading about plasma density or cosmic rays, teaches us how to design the explorers that will one day follow. As the spacecraft drifts farther into the galaxy, it reminds scientists and dreamers alike that humanity's reach has only just begun. For most of history, the idea of leaving the solar system belonged to the realm of myth. Ancient cultures imagined the stars as fixed lights in a distant sky, unreachable and eternal. Even after telescopes revealed the true scale of the cosmos, the distances seemed impossible. Proxima Centauri, the nearest star beyond the Sun, lies over 4 light-years away, more than 25 trillion miles. At Voyager's current speed, about 17 kilometers per second, it would take over 70,000 years to reach that star. For centuries, such spans of time and distance made interstellar travel sound like pure fantasy. But Voyager proved that we can send a machine, however slowly, across those unimaginable gaps. It is still a sublight traveler, but its success gives scientists the courage to imagine faster, more capable successors. The spacecraft has already shown that a probe can survive decades in deep space, communicate across billions of miles, and navigate through regions of radiation, magnetic turbulence, and near absolute cold. These lessons are the foundation for missions now on the drawing board. One of the most promising concepts is the interstellar probe, a mission proposed by researchers at NASA and other space agencies. The idea is to build a spacecraft specifically designed to leave the solar system quickly and explore the interstellar medium in detail. Unlike Voyager, which relied on a lucky planetary alignment for speed, the interstellar probe would launch directly outward, possibly using a powerful rocket or even a gravity assist from Jupiter to reach speeds far greater than Voyager's. Astronauts traveling to Mars or beyond will need protection from cosmic rays, which Voyager has measured in unprecedented detail. Its readings help scientists model how radiation varies with solar activity, how the heliopause shields or exposes travelers, and what kind of shielding spacecraft will require for safe passage. Voyager has also taught planners how to build spacecraft for extreme longevity. Its RTGs, now over 40 years old, continue to generate power despite the relentless decay of their plutonium fuel. Future interstellar missions will likely rely on improved nuclear systems, perhaps advanced RTGs or small fission reactors, to provide steady power for decades. The careful balance of redundancy and simplicity that keeps Voyager alive. Multiple computers but few moving parts, software that can be rewritten across light days of distance, has become a model for designers aiming to build probes that can last a century or more. The golden record bolted to Voyager's side inspires a different kind of planning. It is not a scientific instrument but a message, a declaration that exploration is more than measurement. Future missions will almost certainly carry their own cultural artifacts, updated with new music, images, and languages to represent the Earth of tomorrow. Some scientists imagine digital archives containing entire libraries, DNA samples, or even instructions for contacting Earth across the eons. Voyager proved that such messages can endure. Future explorers will decide what new stories we choose to send. Even as engineers design new hardware, astronomers use Voyager's findings to refine their understanding of the galaxy. The spacecraft's measurements of interstellar plasma density and magnetic field strength help identify the kind of environment future probes will encounter. We now know that the Sun is moving through a region called the local interstellar cloud, a tenuous zone of gas shaped by ancient supernovae. Understanding this neighborhood is critical for predicting the challenges a fast-moving probe will face, from dust collisions to magnetic turbulence. Voyager's slow, steady journey acts as a scout, giving scientists a first look at the conditions that any future starship must endure. These insights feed into discussions about crewed interstellar travel, a dream that still lies far beyond current capabilities, but is no longer pure fantasy. Concepts such as fusion-powered starships, generation ships that carry entire communities, and even speculative ideas like warp drives all benefit from knowing what actually exists beyond the heliosphere. Radiation levels, dust density, and magnetic turbulence are no longer theoretical numbers. They are measured realities, thanks to Voyager. Any future plan to send humans beyond the solar system will begin with the data this small, aging probe has provided. The cultural impact of Voyager's journey is as important as the science. Its steady signals remind humanity that exploration is not a sprint but a marathon measured in decades. Children who watched the launch in 1977 are now grandparents. Yet the spacecraft continues to travel, carrying their era's hopes into a future none of them will see. This continuity encourages planners to think in long timescales, 50-year missions, 100-year engineering lifetimes, projects that will outlast political cycles and economic trends. Voyager proves that patience can pay off, and that a mission begun today can still be sending discoveries to people who have not yet been born. Around the world, scientists and engineers are already laying the groundwork for the next steps. In Europe, proposals for long-duration probes to the outer heliosphere gather support. In the United States, the interstellar probe concept continues to evolve, with studies examining possible launch windows in the 2030s. International collaborations may play a key role, pooling resources to build spacecraft capable of surviving for half a century or more. Each proposal builds on Voyager's legacy, using its successes and failures as a guide. As technology advances, the pace of exploration will quicken. Miniaturized electronics, high-efficiency power systems, and improved communication methods will allow future probes to carry more instruments while consuming less energy. Autonomous navigation systems will enable spacecraft to make decisions without waiting days for instructions from Earth. Advanced propulsion, perhaps solar sails, nuclear thermal rockets, or even experimental fusion drives, could cut travel times dramatically. Each of these innovations draws inspiration from Voyager's proof that long journeys are possible. Yet even as we look forward, Voyager reminds us of the value of simplicity. Its instruments are modest by modern standards, yet they continue to produce world-class science because they were built to last. Future planners must balance the temptation of complex technology with the wisdom of rugged, tested designs. The most sophisticated instruments are useless if they cannot survive decades of radiation and cold. Voyager teaches that durability is itself a kind of innovation. The spacecraft's continuing journey also raises philosophical questions. When we send machines or someday people beyond the sun's influence, what are we truly seeking? Is it knowledge for its own sake, the thrill of discovery, the desire to leave a mark on the universe? Voyager carries no practical benefit to Earth's daily life, yet it captures the imagination of millions. It proves that exploration is an expression of who we are, a statement that curiosity and wonder are as essential to humanity as air and water. As Voyager drifts deeper into interstellar space, it becomes a silent invitation to follow. International collaborations may play a key role, pooling resources to build spacecraft capable of surviving for half a century or more. Each proposal builds on Voyager's legacy, using its successes and failures as a guide. As technology advances, the pace of exploration will quicken. Miniaturized electronics, high-efficiency power systems, and improved communication methods will allow future probes to carry more instruments while consuming less energy. Autonomous navigation systems will enable spacecraft to make decisions without waiting days for instructions from Earth. Advanced propulsion, perhaps solar sails, nuclear thermal rockets, or even experimental fusion drives, could cut travel times dramatically. Each of these innovations draws inspiration from Voyager's proof that long journeys are possible. Yet even as we look forward, Voyager reminds us of the value of simplicity. Its instruments are modest by modern standards, yet they continue to produce world-class science because they were built to last. Future planners must balance the temptation of complex technology with the wisdom of rugged, tested designs. The most sophisticated instruments are useless if they cannot survive decades of radiation and cold. Voyager teaches that durability is itself a kind of innovation. The spacecraft's continuing journey also raises philosophical questions. When we send machines or someday people beyond the sun's influence, what are we truly seeking? Is it knowledge for its own sake, the thrill of discovery, the desire to leave a mark on the universe? Voyager carries no practical benefit to Earth's daily life, yet it captures the imagination of millions. It proves that exploration is an expression of who we are, a statement that curiosity and wonder are as essential to humanity as air and water. As Voyager drifts deeper into interstellar space, it becomes a silent invitation to follow. Its faint signal, taking nearly a day to reach us, is like a lighthouse flashing from the far side of the ocean. Each data packet whispers, "Come and see, come and learn, Come and continue the journey. Scientists and engineers are listening. The plans they make today, whether for an interstellar probe, a laser sail, or a crewed starship, are answers to that call. The road ahead will not be easy. Building a spacecraft to last half a century demands political will, sustained funding, and a global commitment to science. The challenges of radiation, communication, and propulsion remain immense. But Voyager shows that patience and persistence can overcome even cosmic distances. What once seemed impossible, a functioning spacecraft billions of miles from home, is now a proven reality. The next step is to build on that foundation, to move faster and farther, carrying new instruments, new messages, and new dreams into the great dark beyond. One day, perhaps centuries from now, a probe launched by our descendants may overtake Voyager, racing ahead on a path toward the nearest stars. Perhaps it will carry more sophisticated instruments, capable of imaging exoplanets or sampling interstellar clouds in exquisite detail. Perhaps it will even carry a crew, shielded by technology we can barely imagine. When that day comes, the engineers will look back at a small spacecraft launched in 1977 and recognize it as the beginning. Voyager will be their ancestor, the first tiny step across an ocean of stars. Until then, Voyager continues to teach, inspire, and guide. Each faint signal it sends is a reminder that exploration is possible, that distances measured in trillions of miles can be crossed, and that even a fragile machine built with 1970s technology can outlast the boundaries we once believed were permanent. The spacecraft is far from home, but it is not alone. It carries with it the hopes of everyone who ever looked up at the night sky and wondered what lies beyond. The future of interstellar exploration will be written by many hands, but Voyager's signature will be on every page. Its journey is the seed of a new era, a proof that the universe is not closed to us, that we can build machines to wander among the stars, and that our curiosity can leap across generations. As long as its faint signal continues to reach Earth, Voyager whispers of a future where the stars themselves are destinations, not just distant lights in the night. Voyager 1 drifts in a region of space where the sun's influence finally gives way to the wider galaxy. This boundary is not a simple line. It is a vast, shifting frontier filled with invisible forces, charged particles, magnetic waves, and interstellar gas. For decades, scientists could only guess at what this frontier might be like. Now, thanks to Voyager's tireless instruments, we no longer have to imagine. We have measurements. We have proof. And those numbers are rewriting textbooks about how our solar system fits into the Milky Way. Long before it left the sun's protective bubble, Voyager had already revealed surprises. Even within the outer solar system, it recorded bursts of cosmic rays, high-energy particles that travel close to the speed of light. These rays are born in violent events far away, such as exploding stars and the swirling disks around black holes. Scientists expected that as the spacecraft moved outward, the sun's magnetic field would gradually weaken and cosmic rays from the galaxy would grow stronger. They predicted a smooth increase. But the data Voyager sent back told a different story. Instead of a gentle rise, the cosmic rays came in waves, surging and retreating like tides. Something at the edge of the sun's domain was blocking, bending, and sometimes amplifying them in ways no model had fully captured. The future of interstellar exploration will be written by many hands, but Voyager's signature will be on every page. Its journey is the seed of a new era, a proof that the universe is not closed to us, that we can build machines to wander among the stars, and that our curiosity can leap across generations. As long as its faint signal continues to reach Earth, Voyager whispers of a future where the stars themselves are destinations, not just distant lights in the night. Voyager 1 drifts in a region of space where the sun's influence finally gives way to the wider galaxy. This boundary is not a simple line. It is a vast, shifting frontier filled with invisible forces, charged particles, magnetic waves, and interstellar gas. For decades, scientists could only guess at what this frontier might be like. Now, thanks to Voyager's tireless instruments, we no longer have to imagine. We have measurements, we have proof, and those numbers are rewriting textbooks about how our solar system fits into the Milky Way. Long before it left the sun's protective bubble, Voyager had already revealed surprises. Even within the outer solar system, it recorded bursts of cosmic rays, high-energy particles that travel close to the speed of light. These rays are born in violent events far away, such as exploding stars and the swirling disks around black holes. Scientists expected that as the spacecraft moved outward, the sun's magnetic field would gradually weaken and cosmic rays from the galaxy would grow stronger. They predicted a smooth increase. But the data Voyager sent back told a different story. Instead of a gentle rise, the cosmic rays came in waves, surging and retreating like tides. Something at the edge of the sun's domain was blocking, bending, and sometimes amplifying them in ways no model had fully captured. That something turned out to be the heliosphere, a vast bubble inflated by the solar wind, the stream of charged particles continuously flowing from the sun. The heliosphere is our cosmic shield. It deflects a significant portion of galactic cosmic rays, protecting planets and their atmospheres from harmful radiation. But Voyager revealed that this shield is far more complex than scientists imagined. Instead of a neat boundary, the outer heliosphere is layered like an onion, with turbulent regions where the sun's magnetic field twists and reconnects. Voyager crossed zones of intense particle flux, magnetic walls where fields compressed like stretched rubber bands, and pockets of calm that lasted only days before erupting with new bursts of energy. Each measurement forced researchers to rethink how the sun interacts with the galaxy. One of Voyager's most astonishing findings came in 2012, when the spacecraft crossed the heliopause, the true edge of the sun's influence. For years, scientists debated what signs would mark this crossing. Some predicted a sudden drop in solar particles, others a spike in galactic cosmic rays. Voyager gave them both and more. Over the course of a few dramatic days, the spacecraft recorded a sharp fall in solar wind particles and a simultaneous surge in high-energy cosmic rays from the galaxy. Magnetic field readings changed direction, confirming that Voyager had entered interstellar space. For the first time, a human-made object was sailing through the same medium that fills the Milky Way. But the surprises did not stop there. As soon as it crossed into interstellar space, Voyager's plasma instrument, silent for years after a malfunction, unexpectedly came alive during a solar outburst. The blast of energy from the sun excited the surrounding plasma, causing it to ring like a bell. By timing the vibration, scientists could calculate the density of the interstellar medium. They discovered that space beyond the heliosphere is not empty. It contains a thin but surprisingly dense sea of charged particles, far denser than the plasma inside the solar bubble. This was a revelation. Models had predicted a more gradual change. Instead, Voyager showed a sharp boundary, like stepping from thin air into a thick fog. These measurements have deep consequences. Cosmic rays affect everything from the chemistry of planetary atmospheres to the potential habitability of exoplanets. By mapping the strength of this radiation and the shielding effect of the heliosphere, Voyager helps scientists estimate how other star systems protect their planets. The data even refine our understanding of Earth's own climate history, since cosmic rays can influence cloud formation over long timescales. Voyager's readings also reveal clues about the Milky Way's local neighborhood. The spacecraft has entered a region known as the local interstellar cloud, a pocket of gas and dust thought to have been shaped by ancient supernova explosions. By measuring the density and temperature of this cloud, Voyager provides a first-hand look at material that has traveled across the galaxy for millions of years. Its magnetic readings show that the cloud's field lines are more ordered than expected, suggesting that our solar system is moving through a relatively calm zone. Yet even in this calm, Voyager detects subtle ripples, evidence of shock waves from distant stellar events still echoing through space. The magnetic data carry another surprise. Before the crossing, scientists expected the interstellar magnetic field to differ sharply from the Sun's field in both strength and direction. Instead, Voyager found them strangely aligned, almost as if the heliosphere had been twisted to match the surrounding galaxy. This unexpected harmony raises questions about how our solar bubble formed and whether similar alignments might exist around other stars. The discovery hints that the heliosphere is not merely a passive object drifting through the galaxy but an active participant in a larger magnetic dance. These insights do more than satisfy curiosity. They have practical value for future explorers. Any spacecraft or crew venturing beyond the heliosphere will face the full force of galactic cosmic rays. Thanks to Voyager, engineers can now design shielding with real numbers in mind. The data guide predictions about how radiation levels change with solar cycles, how magnetic turbulence might affect navigation, and what kind of communication systems can survive in such an environment. Without Voyager's patient measurements, these calculations would remain guesswork. The spacecraft has also provided unexpected glimpses of solar activity. Even though Voyager is outside the Sun's main influence, it still senses the echo of solar eruptions. When the Sun releases a powerful coronal mass ejection, the shock wave travels outward for over a year before reaching Voyager. When it does, instruments detect sudden rises in plasma density and magnetic pressure. These delayed signals act like a distant weather report, allowing scientists to study solar storms long after they leave the inner solar system. In a way, Voyager serves as a far-flung sentinel, monitoring the Sun from the ultimate outpost. Perhaps the most profound revelation is philosophical. Before Voyager, the boundary of the solar system was a matter of theory. Now it is a place we have visited. We know its size, roughly 120 astronomical units from the Sun at the point where Voyager crossed, and we have tasted the material that lies beyond. We have learned that the galaxy is not an empty void but a dynamic ocean of particles, fields, and energy. Our Sun sails through this ocean, carrying its planets inside a protective bubble that shrinks and swells with each solar cycle. For the first time, humanity has measured the shoreline of this cosmic sea. As Voyager travels deeper, it continues to refine our understanding. Its instruments, though aging, still detect subtle changes in plasma density and magnetic direction. Each variation helps scientists map the texture of interstellar space, whether it is smooth or clumpy, calm or turbulent. Already, Voyager's path has revealed small-scale structures, filaments of denser gas that may trace the remnants of ancient supernova shells. These features tell a story of our galaxy's violent past, where exploding stars sculpt the interstellar medium and create the clouds that someday give birth to new suns. The data also feed into models of how the heliosphere itself will evolve. Over thousands of years, the Sun will drift through different regions of the galaxy, some denser, some more turbulent. Voyager's measurements help predict how these changes will affect the size and strength of the solar bubble. A denser cloud could compress the heliosphere, allowing more cosmic rays to reach Earth and potentially altering our planet's climate. A calmer region might let the bubble expand, offering greater protection. In this way, a tiny spacecraft billions of miles away contributes to understanding the long-term environment of our own world. Even as the probe moves farther, the journey is not endless. Its radioisotope power supply weakens each year. Eventually, instruments will shut down one by one until silence remains. Yet the science will continue long after the last signal fades. The measurements already collected form a baseline for everything that follows. Future missions, such as the proposed interstellar probe, will build on Voyager's map, venturing farther and faster to confirm and extend its discoveries. But Voyager will always be the pioneer, the first to leave the sun's cradle and touch the space between the stars. The revelations from Voyager remind us that exploration is not only about reaching new places, but about seeing familiar things in a new light. Our solar system is not an isolated island, but a ship sailing through a vast, dynamic galaxy. The edge of the heliosphere is not a wall, but a gateway, a permeable boundary where the breath of our star meets the winds of others. By crossing it, Voyager has shown that the universe is more connected, more alive, and more surprising than we dared to believe. Every day, as the faint signal from Voyager travels for nearly 23 hours across the void to reach Earth, it carries a small packet of this truth. Inside that signal are counts of cosmic rays, shifts in magnetic fields, and whispers of interstellar plasma. Together they form a message. The galaxy is not empty. It is rich, structured, and waiting to be explored. Voyager has opened the door. Now it is up to us to follow. While Voyager travels through the darkness, a very different kind of journey continues here on Earth. In a quiet control room at NASA's Jet Propulsion Laboratory in Pasadena, California, engineers and scientists wait for signals that take nearly a full day to cross the void. Each tiny bit of data represents a conversation across billions of miles. The spacecraft is far beyond the reach of any rescue, powered by a fading nuclear heart, yet a small group of humans still listens. They are the caretakers of a machine older than many of the people who now guide it. Their story is as extraordinary as the science Voyager delivers. The mission began in the 1970s, an era of rotary phones and typewriters, when computers filled entire rooms and digital storage meant magnetic tape. Voyager's design reflected that time. Its memory capacity was less than that of a single photo on a modern smartphone. Commands were written in a language of ones and zeros, loaded onto reels, and transmitted through deep space antennas scattered across the planet. When the spacecraft launched in 1977, the engineers knew that keeping it alive for 12 years, the expected lifetime, would be a triumph. Few imagined it would still be operating nearly half a century later. The longevity of the mission has created a rare bond between generations. Some of the original team members have retired or passed away, but their students and successors continue their work. New engineers inherit not just a spacecraft, but a legacy of ingenuity and persistence. They study decades-old schematics, decipher handwritten notes, and learn the quirks of vintage electronics that must be coaxed into action. They become part detective, part historian, and part artist, finding ways to talk to a machine that was never meant to live this long. Daily operations are a delicate dance. Commands must be planned carefully because every instruction takes nearly 22 hours to reach Voyager and another 22 to return. There is no instant feedback, no real-time control. If something goes wrong, the team must wait almost 2 days to see the results of any fix. This delay demands patience and precision. Engineers double-check every sequence, knowing that a single error could end the mission. It is like steering a ship by messages in bottles, each tossed across a cosmic ocean with the hope it will arrive intact. The people who guide Voyager often describe their work as tending a campfire in the dark. Each time they receive a signal, a stream of data showing that instruments are still alive, they feel a surge of warmth and connection. They know that the photons carrying that signal left the spacecraft nearly a day ago, crossing billions of miles at the speed of light. In that faint whisper, they hear not just numbers but the echo of human curiosity, a proof that our reach extends beyond the sun. Voyager's long life has also created challenges few missions ever face. Components fail, power declines, and software written decades ago must be adapted to new realities. Engineers have become masters of creative problem solving. When a memory fault scrambled Voyager 1's ability to send data in 2023, the team devised a daring plan. They moved critical code to a different, still healthy sector of the spacecraft's computer memory. This required precise calculations and a deep understanding of a system older than many of the people working on it. The repair worked, and Voyager began sending clear data again, a triumph of patience and skill. Every decision is shaped by the slow fading of the spacecraft's power source. Voyager's nuclear batteries lose a little strength each year. To keep the probe alive, engineers must turn off instruments one by one, preserving energy for the most essential functions. Each shutdown is bittersweet. Instruments that once recorded magnetic fields, plasma waves, or cosmic rays are carefully powered down, their silent housings drifting through space as the mission continues. The team calls these moments farewell ceremonies, acknowledging the end of a tool's service while celebrating the knowledge it provided. The emotional weight of these choices is heavy. Many engineers have spent decades caring for Voyager, checking its health each day, celebrating its milestones, and worrying over its problems. Some describe the spacecraft as a family member, a distant but beloved relative who sends occasional postcards from the farthest reaches of the universe. They know that one day the signal will stop. They prepare for that inevitability, but none of them truly wants to see it happen. Each successful contact, each new bit of data, feels like a small miracle. Voyager's journey has also inspired countless people outside the mission team. Writers, musicians, artists, and ordinary stargazers see in it a symbol of endurance and hope. The golden record it carries, a time capsule of Earth's sounds, music, and greetings, has become an icon of humanity's desire to be known. School children learn about Voyager and imagine where it might be when they are old. Couples listen to the music encoded on the record and feel part of a larger story. Scientists use its data to refine their models of the galaxy, while dreamers simply marvel that a machine built in the 1970s still speaks across the stars. Among the most moving aspects of the mission is the way it unites people across cultures and generations. Voyager's faint signal is captured by giant radio dishes in California, Spain, and Australia, stations of NASA's Deep Space Network. Engineers in different countries work together to track the spacecraft, exchanging data and solutions. In an age often marked by division, Voyager stands as a quiet reminder that curiosity and wonder belong to everyone. Its message is not limited by borders or languages. It speaks to the shared human urge to explore. The team often reflects on the irony that the spacecraft, so far away, has brought people closer together. They recall nights spent waiting for signals, watching as graphs on computer screens flicker to life. They describe the thrill of hearing the first confirmation that Voyager had crossed into interstellar space, a burst of numbers that carried the weight of history. They remember the long months of silence during technical problems, the tension of troubleshooting across 14 billion miles, and the relief when the spacecraft finally responded. These memories bind them to each other and to the machine they guide. The mission's endurance has forced NASA to rethink how it approaches time. Most space projects operate on short cycles. A few years of planning, a launch, a handful of years of data collection. Voyager spans decades. Some of the people who approved its budget are gone. Some of the scientists who designed its instruments have retired or died. Yet the mission continues, supported by new generations who were not alive when it began. This passing of the torch is a reminder that exploration is larger than any one lifetime. It requires faith that those who come after will continue the work. As the years pass, the connection between Earth and Voyager becomes more fragile. The spacecraft's transmitter grows weaker, and the background noise of the galaxy grows louder. Engineers must carefully tune antennas to capture the faint signal. Each year they wonder how much longer they will be able to hear it. Yet each year, against the odds, Voyager speaks again. The signal is faint but steady, a cosmic heartbeat that reassures its caretakers that the mission lives on. The golden record remains Voyager's most poetic gift. Etched onto a copper disc, it carries greetings in dozens of languages, samples of music from Bach to Chuck Berry, sounds of wind and rain, the laughter of children. It is a message not to any one civilization but to the universe itself. If another intelligence ever finds it, they will hear a snapshot of Earth as it was in the late 20th century. Our voices, our songs, our heartbeat. The idea that a distant being might one day listen to those sounds gives many on the team a sense of connection that transcends space and time. As Voyager moves farther from home, the team faces a future filled with both pride and melancholy. They know the spacecraft will outlast their own lives. Long after its instruments fall silent and its signal fades, Voyager will continue its journey, carrying the golden record through the galaxy for billions of years. It will pass near other stars, perhaps drifting into new clouds of gas, perhaps becoming part of some distant planetary system. No one will be alive to see it, but the knowledge that a piece of Earth travels forever is a comfort and a wonder. For the engineers and scientists who care for it, each day of contact is a gift. They arrive at work knowing they might witness another milestone or perhaps the final whisper. They share stories of their first days on the project, of sleepless nights during critical maneuvers, of the thrill of discovery and the quiet moments of awe. They laugh about the quirks of ancient hardware, about the challenge of maintaining software written before many of them were born. They speak with affection of a spacecraft that has become a companion, a colleague, and, in some ways, a friend. The human story of Voyager is not just about technology. It is about persistence, imagination, and the simple desire to know what lies beyond the next horizon. It is about people who refused to accept limits, who believed that a small machine built with 1970s technology could carry our curiosity into the stars. It is about the generations who keep listening, long after most missions would have been forgotten. Voyager shows that exploration is not a single moment of triumph, but a long, patient conversation with the universe. Even now, as the spacecraft drifts farther into interstellar space, the team continues to send commands and receive data. Each successful contact is celebrated, each challenge met with quiet determination. They know that one day the signal will stop, but they also know that Voyager's journey will never truly end. Its story is now part of humanity's story, a testament to what can happen when people dare to dream beyond the bounds of their own time. When the final signal comes, and there will be sadness but also gratitude. Gratitude for the discoveries, for the decades of wonder, and for the reminder that we are capable of reaching beyond our small world. Voyager will continue on, silent but enduring, carrying the golden record through the endless dark. And somewhere, billions of miles away, a small machine will keep moving forward, proof that the human spirit can cross any distance. Voyager is more than a spacecraft. It is a teacher, a blueprint, and a spark for dreams that stretch far beyond our current reach. Every measurement it sends back, every faint count of cosmic rays, every subtle change in magnetic fields, serves as a quiet instruction for the explorers who will follow. Its journey is a lesson in how to build machines that last, how to survive in deep space, and how to think in timescales longer than a single human life. As its signal grows weaker, its influence only grows stronger, pointing the way to a future where interstellar travel moves from imagination to engineering. When Voyager launched in 1977, the idea of leaving the solar system was mostly poetic. It was a chance to visit the giant planets and then drift quietly into the dark. No one expected a continuing mission in interstellar space. Yet the data that now streams from beyond the sun's protective bubble has become a foundation for planning what comes next. Missions on the drawing board today, some already under serious study, owe their very existence to Voyager's example. The most immediate descendant is the proposed interstellar probe, a spacecraft designed from the start to escape the sun's influence and map the nearby galaxy. Voyager showed that a small craft can survive decades in harsh radiation, extreme cold, and near-vacuum conditions. It also revealed that the edge of the heliosphere is not a smooth shell, but a turbulent region filled with shocks and magnetic knots. The interstellar probe will be built with these lessons in mind. Engineers plan to launch it on a powerful rocket, perhaps assisted by a gravity slingshot around Jupiter, to reach speeds more than twice those of Voyager. Within 50 years, it could travel 1,000 astronomical units from the Sun. 3 times farther than Voyager is expected to reach in the same period. There it could take detailed measurements of the interstellar medium, its chemistry, its density, its hidden magnetic patterns, and give scientists a 3-dimensional map of our galactic neighborhood. Voyager also helps designers understand the demands of power and longevity. Its nuclear batteries, called radioisotope thermoelectric generators, have steadily produced electricity for almost 5 decades. Future probes will likely use updated versions of this technology, with more efficient thermocouples and longer-lived fuel. Voyager's careful power management, shutting down instruments in stages, rationing energy for heaters and transmitters, has become a case study in how to keep a spacecraft alive long after launch. Engineers studying the interstellar probe often describe Voyager as their training manual, a living example of endurance. Beyond uncrewed probes, Voyager shapes ideas for crewed deep space travel. Anyone who dreams of sending humans beyond Mars must consider the radiation environment that Voyager has measured directly. Its readings of cosmic ray intensity and magnetic turbulence help scientists design shielding for spacecraft that might one day carry astronauts through the outer solar system or even on multi-generational voyages to other stars. Without Voyager's data, planners would have to rely on theory. Now they can work with real numbers, tested in the very space where future travelers will go. The spacecraft's crossing of the heliopause has also forced scientists to rethink the protective role of our sun. We now know that the heliosphere acts as a giant magnetic umbrella, blocking a significant fraction of galactic cosmic rays. The size and shape of this bubble depend on the sun's activity and the density of the surrounding interstellar medium. As our star drifts through the Milky Way, it will encounter denser clouds that could shrink the heliosphere, exposing planets, including Earth, to higher radiation levels. Voyager's measurements allow researchers to model these changes and prepare for their effects, whether on future missions or on our own planet's climate over thousands of years. The influence of Voyager extends to the search for life as well. By studying how cosmic rays and magnetic fields shape the chemistry of interstellar space, scientists can better estimate where organic molecules might survive and where they might be destroyed. Voyager's detection of dense interstellar plasma provides clues about how raw material for planets and life circulates through the galaxy. These insights guide telescopes and future probes toward the most promising targets for finding habitable worlds. Meanwhile, visionary projects take inspiration from Voyager to imagine even faster journeys. Concepts such as Breakthrough Starshot propose using giant ground-based lasers to push tiny sail-equipped probes to a significant fraction of the speed of light, allowing them to reach the Alpha Centauri system in just a few decades. Such missions remain theoretical, but Voyager proves that the dream of interstellar exploration can move from science fiction to engineering reality. It shows that with patience, careful planning, and a willingness to work across generations, humanity can send its creations into the deep galaxy. Voyager's lessons are not only technical, they are cultural. The golden record it carries, a copper disc etched with sounds, music, and greetings from Earth, has become a symbol of humanity's desire to communicate across space and time. Future missions will almost certainly include their own messages, perhaps digital libraries containing entire languages, scientific archives, or even DNA samples. Voyager set the precedent. Exploration is not just about gathering data, but about leaving a trace of ourselves for whoever might one day find it. In universities and research centers around the world, Voyager's story inspires students to enter science and engineering. Many of today's mission planners were children when the spacecraft first launched. They grew up watching its encounters with Jupiter and Saturn, then joined NASA or other space agencies to continue the work. They now mentor a younger generation who will design the missions that follow. This passing of inspiration ensures that Voyager's legacy will persist long after the spacecraft itself falls silent. The mission also influences how we think about time. Voyager operates on a scale that stretches human imagination. Commands take nearly a day to reach it, and its journey to the nearest star will last tens of thousands of years. Future missions will demand similar patience. The interstellar probe is planned to last 50 years or more. A laser sail mission to Alpha Centauri might take 20 years to arrive and another 4 years for its data to reach Earth. Voyager teaches that exploration is not a single moment of triumph, but a commitment across generations. It asks us to plant trees whose shade we will never sit under. Engineers studying Voyager's telemetry also gain insight into building machines that can survive the unexpected. Over its decades in space, the spacecraft has faced radiation storms, micrometeoroid impacts, and aging electronics. Time and again, the team on Earth has devised clever software patches and workarounds, even moving code to unused memory banks when hardware began to fail. These stories guide designers of future probes, reminding them to build in redundancy, flexibility, and simplicity. In the cold vacuum between stars, there is no repair shop. A spacecraft must carry its own solutions. Perhaps Voyager's greatest gift is perspective. By measuring the heliosphere and the interstellar medium, it shows that our solar system is not an isolated island but a moving vessel in a vast galactic sea. The sun's magnetic bubble shields our planet, but beyond it lies a dynamic ocean of plasma and cosmic rays shaped by the births and deaths of stars. Understanding this environment is essential not just for exploration but for appreciating our place in the cosmos. It reminds us that Earth is part of a living galaxy, influenced by events light years away. As planners look ahead, they imagine a chain of missions stretching into the future. An interstellar probe in the 2030s, perhaps a laser sail fleet in the 2050s, and eventually crewed voyages centuries from now. Each step will extend the map that Voyager began. Each will carry new instruments, new messages, and new questions. Yet no matter how advanced these missions become, they will all trace their lineage to a pair of 1970 spacecraft that refused to stop. Voyager's legacy even touches philosophy. It forces us to consider what it means to be remembered. Long after Earth's continents shift and its languages change, Voyager will still be traveling. Billions of years from now, when the sun has swollen into a red giant and Earth itself may no longer exist, Voyager will still carry the golden record through the galaxy. Somewhere, perhaps near a distant star, it may drift past a world where intelligent beings wonder who sent it. That possibility, however remote, gives humanity a form of immortality. Our voices, our music, our heartbeat, encoded in a durable disk, will outlive our species. This thought influences how scientists design future messages. Some propose adding not just sounds and images but entire cultural archives. Literature, mathematics, art, even biological blueprints. Others argue for simplicity, fearing that too much information might confuse or overwhelm an unknown finder. Voyager began this debate, and every new mission will continue it. The question is not only what we can send, but what we should send, what aspects of humanity deserve to be our introduction to the cosmos. For all these grand ambitions, Voyager's most enduring lesson may be humility. The spacecraft travels through a universe far larger and older than anything our species has known. Its discoveries reveal forces, magnetic storms, cosmic rays, interstellar clouds that dwarf human concerns. Yet the fact that a small machine built by a young civilization can cross such distances is itself a triumph. It shows that curiosity is powerful, that knowledge can outlive its makers, and that even a tiny signal can bridge an almost infinite gulf. As the faint carrier wave from Voyager continues to reach Earth, scientists and dreamers alike feel a sense of continuity. Each packet of data is not only a scientific measurement but a reminder that exploration is possible. It whispers of a future where interstellar travel is routine, where probes skim past distant stars, and where humans themselves may one day venture beyond the heliosphere. The road will be long, but Voyager has shown that the first step has already been taken. Its journey proves that boundaries are temporary. The edge of the solar system is not the end of space. It is the beginning of a new realm. By crossing it, Voyager has opened a doorway for all who come after. Whether through slow, patient probes or daring light-sail missions, humanity will follow that path. And when those future explorers look back to the moment when interstellar travel truly began, they will see a small spacecraft launched in 1977, carrying a golden record and the restless spirit of Earth. Voyager continues outward, silent except for its steady signal, carrying the lessons of endurance and curiosity. It tells us that we can reach farther than we once believed, that we can build machines to outlast our lifetimes, and that we can send a message to the stars that may one day be heard. This is its legacy. A bridge from the world we know to the universe we have yet to explore, a reminder that the story of human exploration has only just begun. Far beyond the planets, in a place where the sun is just another bright star, Voyager continues its silent flight. It has been traveling for almost 5 decades, moving more than 1 million miles every day. From Earth, it is now so distant that a single command takes nearly 22 hours to arrive, and the faint reply takes the same time to come back. The spacecraft is still alive, but its power is fading. Every year, its nuclear batteries produce a little less electricity. The glow that once ran a dozen instruments is now barely enough to keep a few of them alive. The long goodbye has already begun. Engineers at NASA have spent years planning for this slow decline. They know that each watt of power is precious. Step by step, they have turned off heaters and scientific instruments, choosing carefully which ones to save. The cameras were shut down long ago. Other sensors followed. Each shutdown is like closing a window on a world of discovery. But it is the only way to keep the remaining instruments alive. The goal is to stretch the mission as long as possible, to keep at least 1 or 2 detectors working until the very end. The team watches every voltage reading, every temperature report, searching for signs of trouble. The spacecraft is old. Its electronics were built in the 1970s, long before modern computers. Circuits that have survived decades of radiation are brittle. Memory bits can flip without warning. A cosmic ray can upset a processor or scramble a data packet. When that happens, the engineers respond with quiet precision. They write new instructions, test them on simulators, and send them across the void. Then they wait for the signal to return, sometimes for nearly 2 days. Each fix is a triumph of patience and skill, but everyone knows that one day there will be a problem that cannot be fixed. The slow loss of instruments is not just a technical challenge. It is an emotional one. Many of the people who work on Voyager have spent their entire careers with the mission. Some joined when they were young scientists or engineers. Now they are approaching retirement, and the spacecraft they helped launch is still out there, carrying their work into interstellar space. Each time an instrument is shut down, it feels like saying goodbye to an old friend. They know that someday even the transmitter will go silent, and the mission that has defined their professional lives will truly end. The team has already planned for that final moment. Long before the last watt is gone, Voyager will no longer be able to power its transmitter. When the carrier wave stops, there will be no signal to track, no heartbeat to follow. Earth's giant radio dishes will keep listening for a while, sweeping the sky in case the spacecraft manages a brief whisper. But eventually the network will turn to other missions, and Voyager will slip into quiet darkness. It will become a silent traveler, still moving outward at more than 30,000 miles per hour, but with no way to speak. Even after contact is lost, Voyager's journey will continue. The spacecraft will keep coasting through the galaxy for billions of years. Long after the sun has grown into a red giant and Earth itself is unrecognizable, Voyager will still be moving among the stars. It will pass near other systems, drifting through clouds of gas and dust, untouched by time except for the slow erosion of micrometeoroid impacts. Its golden record, protected by a thin layer of aluminum, may remain intact for eons. If another civilization ever finds it, they may hear the sounds of our planet. Greetings in dozens of languages, music from around the world, the heartbeat of a mother and child. Knowing that the spacecraft will outlast humanity changes how we think about time. Voyager teaches that a human lifetime is only a moment in the story of the universe. The people who built it will not live to see its ultimate destination. They launched it with the understanding that it would outlive them, carrying their work and their message far beyond the reach of any future contact. In a way, Voyager is a monument not of stone but of purpose, a statement that curiosity can last longer than those who feel it. The last years of contact will bring their own discoveries. Even as power fades, Voyager continues to measure the density of interstellar plasma, the strength of magnetic fields, and the intensity of cosmic rays. Each new data point adds to our understanding of the environment outside the heliosphere. Scientists hope to keep at least one instrument active until around 2030. After that, the spacecraft will likely be too weak to send useful information. But until the very end, every packet of data is valuable. Even a single reading can refine models of how the heliosphere interacts with the galaxy. The fading signal is a reminder of how fragile communication across space can be. At its current distance, Voyager's transmitter, barely as powerful as a refrigerator light bulb, sends a signal that reaches Earth as a whisper billions of times weaker than a cell phone call. Only the largest radio antennas can detect it. As the spacecraft moves farther away, the signal will grow even weaker. Engineers are already pushing the limits of their equipment to hear it. They use advanced software to sift the faint carrier wave from background noise. Each time they succeed, it feels like catching a single snowflake in a storm. When the final signal arrives, it will be both an ending and a beginning. The spacecraft will no longer send data, but its silent presence will continue to influence science and culture. Future missions, interstellar probe, laser sail concepts, and others yet to be imagined will build on Voyager's discoveries. Artists, writers, and dreamers will continue to find meaning in its journey. The golden record will keep traveling, carrying the sounds of Earth to places we will never see. In that sense, Voyager will never truly be lost. The final years of Voyager also force us to confront our own place in the universe. The spacecraft is a small machine built by a young species on a single planet around an ordinary star. Yet it has traveled farther than any object we have ever made. It shows that even a civilization bound by gravity can reach beyond its home, can send a message to the stars, can create something that lasts far beyond the span of human memory. The silence will not be a failure, but a confirmation of success. The mission was always to travel outward, to keep going, to explore as long as possible. That mission will continue even after the radio goes dark. One day, long after contact is lost, Voyager will pass near another star. It may happen in 40,000 years, when the spacecraft approaches a small red dwarf in the constellation Camelopardalis. From there, it will keep moving, perhaps wandering through the Milky Way for billions of years. It may drift into the distant future, when galaxies merge and stars fade. The golden record will still be there, carrying our greetings across time and space. Whether anyone ever finds it does not matter. The act of sending it was the important thing. For the engineers and scientists who still listen to Voyager, each day of contact is a gift. They know that the end is coming, but they also know that every extra day extends the mission's record as the longest-running spacecraft in history. Each new transmission is a reminder of what humans can achieve with patience and determination. As they plan for the final shutdowns, they also celebrate the extraordinary success that has already been achieved. Voyager's story will not end with silence. It will live on in the data it has sent back, in the maps of the heliosphere, in the understanding of cosmic rays and interstellar plasma. It will live on in the missions it inspires and in the dreams of those who look at the night sky and wonder what lies beyond. It will live on in the golden record, a small disk carrying the essence of Earth across the galaxy. And it will live on in the simple fact that humanity once built a machine that escaped the sun and kept going. As the final watts of power drain from its batteries, Voyager will continue to drift outward, a silent messenger from a blue planet around a yellow star. Long after the last human voice has faded, it will still be there, moving through the endless dark, carrying our story to the stars. Voyager continues its lonely journey beyond the sun's protective bubble, a silent witness to the vastness of space. Long after its signal fades, the spacecraft will keep traveling among the stars, carrying the golden record and the hopes of the world that built it. It proves that curiosity can outlast generations and that even a small machine from a distant planet can leave a mark on the galaxy. Its mission shows us that exploration does not end with silence. It lives on in the path it opened and in the endless questions it leaves behind.